Now, in this investigation, as you built the cube, you found out that the cube would go through and would work very well sometimes, but not as well in others. We could go in, and if we placed a load, and we went and placed our load, I'm going to show it right here. We're going to draw it in, and we pushed in, say, here. Whoops, that's backwards. I'm going to redo that. We pushed in this way onto the structure, it would push over. That didn't do real well. And if we applied a load, say, laterally this way or at an angle, again, didn't fare so well. Especially didn't fare so well if you went in and you applied your load, you applied a shear load. So we went in, applied some pressure here, and we applied pressure here. The load wouldn't do real well. It would bend over and push over sideways. But you did find that in one instance it did work very well. If you applied all of your load vertically down and it was able to come down evenly down the connecting rods, it would hold up very well and would hold well. The only breaking point would be once the connectors couldn't hold it, and you found that it really depended upon way the connectors were oriented. So you need to make sure your connections and take that into account as you build future structures. Which way are my connectors going and which way are the loads going? That will be important for you. So make note of that, to pay attention to the joints and which way the loads are being applied to that joint. It will become very important. But you saw that the square could do well in some cases, and that's something you need to pay attention to. Okay, as we go through this, I want you to make sure you've answered a couple of questions as we finished it. First off, did the structure behave the way it was predicted? If it did not, why? Why do you think the structure would behave in the way you predicted? Why did that happen? And then finally, how might you make your cubes into stronger structures? Now, we're going to come into the next part, and you're going to be adding pieces to it. You're going to try to triangulate it and see if you can't make it just a little bit stronger, and that's what the focus of the next part is. So we're going to go in, and I'm going to show you some parts, and we're going to draw out a few parts and look at how we could make this even stronger than we did before. So let me get my original line back up here. We go in, we make our cube. And it's not perfect, but it does work. There we go. So now we got our cube, and we're going to add in a couple of new pieces. And let's say we come in and we add a piece here diagonally, and we add a piece here diagonally. And then what I want you to do is look at things such as this, and what had happened and what went on as we added that. So how could this be, how does this strengthen it and how does it support it? Well, a lot of it has to do with adding in points, again, where you can get the pieces under tension and compression at the same time, and you transfer the forces along to move them to places where they're better suited. So we're going to come in and look, and if we come in and we apply a force, and let's put a force on here, and let's apply our force this way. So we come in, our force is being applied that way, and we look at it. This is going to try to bend and push the cube over. And as it pushes it over, these pieces go under tension now because this is being pushed out. So this goes under tension here. That's under tension. And since we're pushing across, this is coming under compression. You can see how the pieces start to form together, and they move the forces along throughout the box and evenly distributed so that it can't move away and gets everything locked up nice and neatly and cleanly. So you can see again how the triangulation helps you. You can also get a similar effect instead of using just a single beam coming across if you used your wires. So you could put ropes in there, and we're going to put in a rope, and I'm going to do it a slightly different line just so you can see that it's different. And we're going to add our rope in, and let's say we put it along the top, and instead this time of putting just one line in across this way, we come in there and we come across, and now we've actually strengthened it again. We haven't added a lot of weight, and we haven't added a lot of materials to it. So this actually is, again, it's a way to triangulate it without adding much cost to your structure and making it difficult to work with. Now, as we go in and we look at this, it's important to note why these different changes happen and what's going on, and also think about it as we apply this to the real world. What would happen to this bridge if it was in the real world and we were really using it and we put real forces on it? So I'm going to go back, we're going to draw this piece in, and we've got our frame here. And there's also another way to really, you saw earlier, you could add the cards and add whole solid pieces to it, and you could greatly increase the structure's strength. But what's the problem with that in the real world? What if you have a wind blowing in across, and you've got a rather large wind, so we're going to draw it with a large arrow. You got a large wind blowing in this way. Well, if the structure is solid all the way through, it's going to blow over very easily. It's going to be very, very susceptible to those winds and be damaged very easily. You can see that in trees and houses and things during high winds and tornadoes and such. But if you come in with if you come in and put beams in there, the beams don't take up as much space, but they still do take up quite a bit of space. If you're able to come in and you're able to put in wires, put in tension wires through there, you can add a lot of structure to it, and that is really, really big. You can add a lot of structure to it, a lot of strength to the structure, but you notice that the profile of it is extremely small. These wires add a lot of strength and support the structure great, add a lot of triangulation. Again, the weight is not high, the cost is not high, it's easy to implement, and even more so, there's very, very little face side to it. There's very little surface area, so the wind will just blow through it and won't affect the structure as much, and you get a very strong structure that can last up in the elements. And that's something that's really important as you look forward and we go through these next exercises. And as we finished up the challenge activity where you built the longest spanning bridge you could, but we first did it without triangulation and then we did it with triangulation, something that should have started popping into your mind, you started seeing, and it's a ratio that builders use, and it's called a span to depth ratio. And it's no more complex than that. It's the span of the bridge divided by the depth, and that gives you a ratio. And engineers, depending on the materials they're using or the area they're working in or the safety factor they're looking for, will have some ratio. And let's say our span to depth ratio is a factor of 12. Well, as we increase our span, this means that our span can be no more than 12 times the depth of the bridge. So if our span is 12 meters long, our depth of the bridge has to be 1 meter. Well, if you want to span a bridge that's twice that, let's say 24 meters, well, then your depth needs to double and move to 2. This is a ratio that engineers use, and they look at it to give them a starting point to figure out the safety loads and the factors for their bridge and how long it's going to be, how deep it's going to be, and give them an idea of the materials they're going to be using and what they have to work with. Again, this number 12, I've just pulled a number out. These numbers, what the ratio has to be, depends again upon the materials you're using and safety factors and the environment that you're working in. So keep that in mind, and also don't forget to keep track of that, your span to depth ratio.